So, Prathamesh, one quick point before you start. Uh, I've told Waka to play with the Mastic toolkit, with the cache level attacks, and I told him to recreate them using any simulator like Sniper. Okay, so if it sounds interesting to you, you can also pitch in there.
Yeah, sure. I will talk with Avakar also.
Yeah, and Upasana also has a good hand on Sniper, so Vakar, you can include her with that. Yeah,
Yeah, sure, sir.
yeah. Okay,
Yeah,
Prathamesh, up to you.
yeah. Okay. Thank you, Kalyan. So good afternoon, everyone. So I am Prathamesh, and today I will be presenting the paper CEASER, which appeared in Micro 2018. So just a quick background of what we are looking at. So the modern processors have a hierarchy of cache memories. Is my voice audible or is there any break?
Yeah, it's clear, Prathamesh.
Yeah, okay, thank you. So all the modern processors have a hierarchy of cache memories, and as we all know that the last level cache is shared between all the cores to effectively utilize the cache space, and sharing the cache can lead to conflict based attacks. So just let me on the pointer. So here we can see a typical hierarchy of caches where L1 and L2 being private to each core, and the typical last level cache which is shared with all the cores. So here in this example we are assuming at two core system. So when we look at the last level cache, we see both the cores, applications running on both the cores are sharing the cache, right? So here it is a possibility of a conflict based attacks. So what do we really mean by this conflict based attacks is an adversary can learn the access pattern of core running applications, and he can carefully come up with an algorithm so that he can make the evictions, right? So this is a typical architecture which we are looking at for this particular session. So what are the prior approaches for this randomization kind of thing? So there were some papers which are looking at operating system support based techniques, which they maintain intensive tables for the remapping of the cache blocks, and there was too much dependency on the operating system, which is not fine, because too much dependency on operating system, it gives a control to the OS that whether the particular application is an attacker or a victim based, which is very difficult. So the accuracy is very low here. And the goal of the paper is to mitigate the conflict based attacks without any operating system support. So this is the base which we are looking at. So a
Prathamesh,
quick,
just one quick question here.
yeah.
The cache levels are not visible to the OS anyways, right? So the prior techniques you mentioned were taking support of OS. So in what specific context were they taking OS help?
Yeah. So that question is very true. So what they were doing is they were this mapping was done with the main memory is mapped on last level cache, right? So they were creating clusters there. Whenever it was mapping from the main memory to the LLC, the OS comes in and it creates some clusters, and then it puts the particular application for in that set and other set. So it was doing in that way.
Uh, so what do you mean by creating mapping from main memory to LLC?
No. So just like if there are if there is a four core system, right? So there let's assume there are four different applications which are running on each core.
Okay.
So at the cache, a last level cache is shared. So what the OS based techniques will be doing is they will create a cluster, and then they will assign four, let's say, four ways to this particular cluster and 10 ways to that particular cluster. And
No, but
whenever
the
they
cache is not visible to the OS. So I'm just wondering how is the split happening?
No, actually, they are giving these hints to, they are penetrating these hints. They are giving some bits from down from the, to the ISA level and all.
Okay.
Yeah, they are changing the entire architecture there. So
Okay.
that's why they are proposing that without changing much on architecture, let's try to do it in the hardware itself.
Fine. Okay. Continue.
Yeah, okay, thank you. So just a quick point in the timing-based difference attack. So this is the critical aspect of, uh, any side channel attacks we are trying to stop based on the conflicts. So let's assume there are two-way and two-set cache, and A and B is there. So what the attacker will do is attacker will place blocks A and B in the cache. So just a quick point, in this presentation we can interchangeably use the words lines and blocks, right? So they both will mean the same. So what the attacker will do, it will place A and B into its sets. Now what he will do, he will stay calm for some time. So what then it will happen is, if a victim is accessing that particular set, let's say set 0, so the victim V will insert his own block in that set, and as the set is already full, we have to find a victim. So let's assume that B is chosen as a victim, right? So when B is chosen, what this V will do is, it will insert his own block, right? So now the B is evicted. So now attacker was silent for some time. Now what attacker will do here is, attacker will again access the blocks A and B, right? So when it will again access the block, when he will see the particular block A in the cache set, it is a hit, right? So whenever it is a hit, an attacker will get a quicker response, a faster response. So that means the victim has not evicted that particular set. But when the attacker will search for block B, because he was the one who brought it in the first place, right? So the attacker brought B in the first place, A and B both. Now he is again searching for it. But now as B is not there, B is a miss, and hence it will take long time, as it will need to be fetched from the main memory. So here the attacker gets to know which set the victim is using, right? So although in the real system, when there are more than one what we can say normal processes apart from victim, this becomes much more challenging. So there is a lot of noise there, but we are not looking currently in that situation. So the point which I am trying to make here is, the attacker has used a timing difference to know whether the victim has accessed set 0 or not. That is a particular set. So here comes the definition of a eviction set in this paper. The eviction set means the blocks which are accessing this particular set, and an attacker is successfully able to know whether the victim has accessed it or not. So in this example, block A, B and V will form an eviction set. So what is the culprit here? So the culprit is the set indexing function, right? Now to make attack successful, adversary must find the lines that map to the same set. So this is very crucial here. And in a typical last level cache, the access is done using physical line address, which is the physical address. And the convention LLC design, it uses a static hash function. So no matter how complicated the hash function may be, it is just a matter of time. An attacker will run sophisticated algorithms to reverse engineering, to do a reverse engineering of which particular hash function it is using. And once the attacker is in good knowledge about the particular hash function, he can purposefully create a eviction set, so that he can try to know the victim's access patterns. And the more danger part here is, if one machine's hashing function is known, each and every other machine is vulnerable, because this is hardware, and the production is done at a lock, stock and barrel. So it is not like it is changing from machines to different CPUs to CPUs. So this is the part where we have to look at. Now, what are some key insights here? So the key insight is,
Prathamesh, just one. If you pause for a minute. So others, did you get clarity on the threat model for this particular attack? So what is the entire process that the adversary is going to follow, and what are his access points, right? Did you get clarity on that? This is the right time, because now Prathamesh is going to dive into further details based on this. Okay. Yeah, fine. Prathamesh, continue.
yeah, okay, thank you. Yeah, so I hope we are able to follow here what the threat model is. And so the key insight is, just to repeat, the set indexing function is somehow been able to, the attacker is able to manipulate it at its own wish. Not manipulate it, but actually take help from it and create an eviction set, right? As we have seen earlier. So now what will happen is, now we are looking at randomization. So the point is, let's try to somehow change the mapping of the set indexing function, so that not every time the same block will be mapped to the same set. So let's try to break the point where attacker is trying to take the leverage, right? So let's make it very difficult for an attacker to create an eviction set. So the paper introduces a low latency block cipher, which we will address as LLBC, which is used for encryption and decryption. So here encryption and decryption means the last level cache is operated on physical line address, which is PLA. So what we are trying to do, we are trying to convert it into an encrypted line address. So as we go on, it will be more clear what this encrypted line address is actually. So let's look at the mapping of blocks. Fine. So this is the block address, which is also line address. So there is a hash in a typical cache. They use this hash function, and this is the physical line address in a typical cache, and this is a set associative cache, and these are the blocks which are already present here. So this is a traditional cache, right? So now this A and E, as it is a conflict, right? So this A and E are sharing this particular set. So this particular, let's assume that this is a eviction set. This is a traditional cache. Now, when we are looking at, this encryption based, this is the low level block cipher, which they are using for encryption. And this is the important point. So they are, generating a random key. So here the hash function was, pretty much fixed, no matter how complicated it is. Now they will be generating a random key value, which will be given to this low latency block cipher. And then this physical line address, this gets converted into this encrypted line address. And this is the paper C's, so what they will do is, now you can see, I have the paper was also particularly mentioned here, C dash. What we mean is, now it is indexed by the key. So now you can see, earlier the eviction set was A and E, which means block A and E were sharing a set, but now blocks B dash, like B and D are sharing the set, right? So if we can somehow transform this particular cache state into this state, it becomes difficult for an attacker, because if we keep on changing this, it is very difficult to reverse engineering, or look for the particular sets which are sharing the block. So let's see, operating cache on an encrypted address space, like how this works. So
Hello,
so
Prathamesh.
yeah.
Sorry to interrupt, but so the first slide which you showed, the attacker is accessing set 0, and it is inputting A and B data, right?
Right.
So I'm confused, like, because in this case the attacker already knows that it's set 0, right? Because it's not inserting any data into set 1. So then what are you trying to, like, attacker already knows the set 0, right?
Okay, sure. Let me fill in some part here. So the attacker can potentially do fill blocks in all the sets. Okay, and
Okay.
for every let's say 1 second, he will go and access all the blocks. This would
Yeah.
imagine a loop, and he will try to access after n number of cycles, and he will know based on the access latency whether which sets have missing blocks. It's not
Okay,
here.
but
Prathamesh was taking as set 0 as an example only.
okay, but
Yeah.
but if in that case, if it is entering data into all sets, then whatever whatever encryption algorithm we are trying to get, if it's entering data into all the sets, then it should not matter, right? Because it will.
So the okay, you got the right point when I said all the sets. So it's quite nearly impossible to fill the entire cache, because the LLC which we are talking about will have typically 4096 or 8192 sets cross 8 way or 16 ways. It's a huge space, right? And what typically the attacker would do is he will pick few sets and fill the blocks into them, not all of them.
Okay.
Now
Okay.
with Prathamesh, you can correct me. So with this encrypted mapping, those sets keep changing.
Okay. Okay.
Yeah, Prathamesh, you can correct me.
No, yeah, that's right. Yeah, exactly. So yeah, so your question was, Keshav, your question is right. But as mentioned by Kalyan, yeah, so he, it's very difficult to fill the entire LLC space. So he comes up with a strategy to, quickly make the attack possible. Otherwise, it's very difficult to create an attack also.
Yeah. Yeah.
Yeah. Is your question the answer?
Yes.
Yeah. Okay. Thank you. So, so we were here. So the Keshav, the point is, so attacker is exploiting this idea that A and E, they are sharing the blocks. So for example, I'm taking A and E. It can be any number of, any blocks. So if the mapping is static, right? So the attacker, after some time, he can, reverse engineering which particular blocks are accessing to that set, right? So now he can take advantage based on the timing based attacks, right? So the idea is, as explained by Kalyan, let's try to change this mapping from physical to encrypted so that this mapping gets changed, right? Now if the mapping is changed, you see that B and D are sharing the cache set, right? So if any eviction, if the attacker tries to create, reverse engineering this particular set, he gets the wrong value, right? So the attack is not created. And we will again look into much more deeper, what are the deeper nuances of this approach also, how attacker can still exploit if the mapping is still changed, right? So yeah, so let's look at some basic operations of how a cache is being operated on encrypted address space, right? So this is a typical last level cache. So this is the physical line address. If there is no encryption, the PLA will directly be indexed to the LLC. But now here we are doing the encryption with a random key which is generated, right? Then there will be ELA, that is the encrypted line address, right? So the basic point which the paper tries to do is, it tries to isolate this last level cache, and only the last level cache is operating on encrypted address space. So anything above, so above LLC will be L2 and below LLC will be the main memory, right? So these two, they don't know a thing about what is encrypted address space. It is completely isolated. So what it will do, so yeah, we will look into deep when this will happen. So only the LLC is operated on the evicted encryption address space. The rest of the system does not know about the ELA. And let's take an example of a dirty block, right? So let's see what happens. So if we have indexed with the ELA and there is no space for that particular block, right? So we have to kick some block out and then we have to make space for this block, right? So whatever is our victim block, when we are evicting it, right, it is still having the encrypted line address, right, which is not known to the main memory. So what we try to do is, we have to use a decryption function, which is the low LLBC decryption function, which will convert this ELA again to PLA, and then this B will be, this writebacks and dirty evicts will be happening in the main memory, right? So this is completely isolated. So now here is the point, this encryption and decryption is happening on a critical path, right, as you can see. So every time we are accessing LLC, there is an encryption. Every time there is something which is evicted from LLC, there is a decryption, right? So although they have used this low latency block cipher, still in the paper they have mentioned that it takes 2 to 3 cycles for them to do this. And a typical last level cache access takes roughly 20 to 25 cycles. It depends upon the cache size, but roughly the value is that. So nearly it consumes 10% of the LLC access time, this encryption and decryption, even if we are going with the low latency block cipher, right? So this is the phenomena that the entire LLC is isolated.
Okay, so Prathamesh, a side question here. So
Yeah,
when such an attack is staged, right? At
right.
least what the authors were studying. right? Do they consider LLC as a single chunk, meaning one huge chunk of LLC, or is it considered as banks or anything like
Yeah,
that?
yeah, yeah. So actually,
Hmm.
they have given their analysis on both the implementations. They have
Okay.
considered LLC as a whole chunk also, and then they say that they consider it as a at bank level also. But then
Okay.
this, if we consider LLC at bank level, then this encryption and decryption has to happen at the bank level.
Right, right. Okay, that point is okay. I'm even talking the one step before it when they stage the attack, right?
Hmm.
How did they consider? I mean, it's a single chunk or a bank because the attack itself would need to change, right? Based on the number of banks, etc.
Yeah, yeah. So what they mention in the paper is, yeah, your point is absolutely right. When they shift to the banked LLC, they say, that as we know, the number of sets have reduced, right? So
Hmm.
the remapping rate has to be changed accordingly. But they say that their remapping rate, is sufficient to handle it. But ideally, as per your point, the remapping rate should be, decreased. Like after very small accesses, we have to remap the cache because now the number of sets are slow. So there is a bigger window for an attacker to, deploy this attack.
Yeah, makes sense. Makes sense.
Yeah,
Okay, go
yeah,
ahead.
yeah. Okay, thank you. So, so you know, so let's tackle one more question. Now you may also be guessing this, that whether this encryption line address and key, just inserting this key, does it solve the problem? So the point is, if this key is also static, so attacker can figure it out this also. It's not a big deal for an attacker. If this key is, although it is randomly generated, but still attacker can, figure it out. Because it's just the matter of reverse engineering. It will just take more time as compared to hash function, but it is still reconfigurable. So the important point is it still sufficient? So this was just the C's part out of Caesar. The R is still missing here. So what is it? So let's try to see what happens. So the point is the attacker can still create an eviction set if the key stays same for a long time. So what the paper proposes is change the key, change the key and remap it again. So this process which we have done, we have to do it in a continuous loop fashion. So let's see how the paper tries to, tackle this issue. So, so here is a line address, and there is a LLBC, low level block cipher. So now it is mapped with key 2 after some time, right? So we will go into much more detail how this happens, but after some time it is again mapped with key T2. Now, now let's say, it again generates an encrypted line address and the blocks are, again mapped. So it's B double dash, right? So now what was happening earlier is B and D were sharing a set. Now what will happen is now C and A are sharing the set, right? So when we introduce this one more key, so if we go on doing this process, now this becomes really difficult. So this is the catch here. Now here comes the R part from the Caesar. So the R part is eviction set has already changed, and after, let's say, it was time T1 and now time has progressed T2. So the R part is the dynamic remapping. So the dynamic remapping is very essential. Now we will again go into some examples of how it is done, but this is the whole picture. So anyone has any question till this point? Is the basic flow understandable, or should I repeat some points?
Hello, yes. The key is extracted or does the mapping is extracted by the attacker? Because
Uh,
if the key is itself known, so what remapping will change? Because it can
uh,
again get the key T2. So is
uh,
the key attacker knows the key by attacking or just knows the final mapping after the ELA, what the eviction sets are forming?
yeah, yeah. Yeah, it's a good question, Navneet. So the key is completely unknown to the attacker, right? It is a randomly generated value in the hardware, right? So the attacker doesn't know what is this ELA, but it can guess it after some more time. and not the ELA value, but the sharing of the set. You got it, Navneet? So the
Yes.
attacker doesn't know the key. It after some time, if this if this key remains the same, what attacker will do is again try to insert his own sets and wait for some time. The timing based attacks, right?
Okay, okay, I got it.
Yeah. So the timing if this remains same for more than a particular window, the timing based attacks will again come into picture, right?
Okay, I got it.
Yeah, so this sharing of the set we have to break. So let's say if here attacker tries to put his own sets, right? This B and D, right? Now if he waits for some time, he if he assumes that the attacker is going to insert his own value, but now the mapping has changed after some time, right? So now if he is looking for B and D, he will get the wrong value. Is your question answered, Navneet?
Yes, but yes.
Yeah.
Prathamesh, I'm having one question.
Yes, yes, Okar.
Yeah, you are saying that after every time, for example, after every second, the key is getting changed, right? So,
Mm-hmm.
isn't it possible that we can predict the key also?
No, no. Keys are generated with the help of random number generator.
Okay.
Yeah. Key is not predictable. Yeah. Okay. So, so what
Prathamesh,
is?
a quick point
Yeah.
here. This is,
Yeah.
for everyone. See, what the attacker is trying to do here is uh, try trying to fill up the shared resource with his own data here, right? And then he is polling on it every now and then and seeing whether it's present or not, etc. Right? And from based on that, he's trying to make some inference. Now, so do you think we can stage such an attack at main memory and secondary memory also, or let's say even at the page table? What do you think? It's open for everybody.
Yeah. So, yeah, Keshav, you want to say
Um,
something?
so, but the difference is that in cache,
Hmm.
some data needs to be evicted, right? But that's not the case with the secondary memory.
Okay, good.
So, I mean, the attacker can try, but the mechanism would be different. That's what I'm thinking right now.
That's a valid point only. So we need to refine the attacks specifically for storage, right? And a connected point that I think of is we have the flash translation layer anyways in place, right? In what it's basically doing is it's trying to map the blocks, right? The logical and physical blocks. So if we want to build uh, a defense, we can directly go ahead and make the FTL itself uh, pick the mappings at random or some after change it every few intervals, right? Okay,
Yeah.
what about
Also,
others? Yeah,
yeah.
go on,
One
Keshav.
more point also. So here, I think the attacker is also trying to guess which core is accessing like the set, right? But I think in
Mhm.
the storage, if the attacker can access the storage, that's the biggest issue, right? For in the first place.
No, but the attacker data will also be part of the storage. Why not?
Yeah, the
Okay.
attacker's data will also be part. Yeah, so one small point I would like to make, Kalyan, regarding your
Mm,
question.
mm,
So you mentioned about main memory and SSGs.
mm,
So the key thing for this kind of timing-based attacks is, let's say let's say about this particular attack, which we are looking for. So here what the attacker has done is it has placed his own block and
mm.
then it is waiting for some time, right?
Right.
Now it again has to access this his own blocks, but if
Mm,
his access gets filtered by the upper levels of caches, right? the attack itself is not possible. So he has to, somehow bypass or, create a working set in which his accesses to the upper levels are filtered. So
But
if,
Prathamesh, here the this part is already kind of to an extent handled by even this uh, attack at LLC also, because the request will come only if he has crossed L1 and L2. In the same way, at the memory we'll say that it has crossed L3 also.
yeah, but then, coming up with that kind of access pattern, it's just a guess, I think would be challenging.
Okay.
The deeper we go into the memory hierarchy, I think, stage, because L1 and L2 are small, LLC is comparatively bigger. But I think if we have to stage such kind of attacks for main memory, to generate miss all the time at higher levels, no, it's easy if we just write a for loop which is having, yeah, I think it is possible.
See, all we have to do is generate an address which is beyond one page size, typically 4 kilobyte or 8 kilobyte. How
Right,
difficult is it, right?
right.
Yeah. So, like Keshav said, but no, even for the main memory, we need to change the attack uh, um, so that we are trying to refer to the same page across, multiple intervals, and we are trying to see whether that particular page is still open at the bank or not, etc., etc. Right?
Yeah, yeah, yeah.
These are the details. But what I'm trying to ask is, uh, some in similar line, if this attack is as such possible or not. Yes, implementation requires some more effort. Why is cache so lucrative here? So that's what I want to arrive at.
So,
What?
sir,
Uh-huh.
Dr. Kalan, at main memory, the OS concept will come to play, like the address space, like the one process address space will not be shared with the other process.
The same
That
thing
will,
is here also.
Yeah, the same thing is here also.
Wakar, I'm not sure if I answered your question.
like
You can
I was
explain.
saying, I'm saying is that like at the main memory particularly, one process address space will not be interfered with by the another process.
That's true, but they can both still access the same bank.
Yes,
Yeah.
yes, yeah.
Yeah, I think it this requires, much more level of sophisticated, deep thinking about this, I think.
So the reason I ask this question is, when you try to link some particular attack at any particular, any specific hardware component, pick other components which look similar like this and try to see if this attack can be replicated there or not. Okay. In the
Yeah,
process, you will know more about what is the attacker's strength at the cache. What is his strength? The biggest strength is the space is quite limited, and he's trying to generate addresses which are just one block apart, 64 bytes apart.
right,
Right. So this granularity will increase as we go from to the main memory
right,
and eventually to the storage. On
right,
top of
right.
it, staging such an attack even is even more challenging, because the timing gets messed up a lot at the
Yeah,
memory and storage. They
right,
are already slow operations, right?
right,
Of course, we can go and say some particular page is a miss at the memory, but that will change the access latency only by, like, let's say 15-20 cycles.
right. Uh-huh. Yeah,
Detecting that 15-20 cycles at the core is another big challenge the attacker would have.
right, right.
So if,
Yeah,
I want you guys to do such an analysis, existing attacks, why it would work there, why is it not working here, etc., etc. This analysis will help us in two ways. One is staging new attacks. Two, we can propose better defenses.
yeah, yeah, got it.
Okay. Any other thoughts, others? What about page table?
Yeah, actually on page table, I have a small comment here. Regarding a page table, actually to successfully deploy this kind of attacks also, they are somehow changing the not the page table but the page sizes. The page size has to be dynamically changed. I think in a couple of first lectures I asked you this question that I was having a doubt regarding how because the processor will generate virtual addresses, right? But the LLC is been accessed by the physical address.
Right.
So how an attacker can confidently create an eviction set, right? So because not all the bits are visible when the translation takes from virtual address to physical address,
Right.
not all the bits are visible. So what they do is they purposefully try to generate the page misses, that is at the main memory. So what they will do, so what the OS will do, a modern OS which is latest one, what they will do is they will see that, oh, there are many page misses, so they will dynamically create pages of more sizes.
Okay.
So when the page size is increased, uh, so automatically more bits are visible here. So when because the page size, what we say,
The page offset.
yeah, the offset is fixed, right?
Right.
But the remaining bits are variable. So if we can change page size dynamically, so they write this kind of code, so when the operating system is being tricked that the process is not getting hit, it increases its page size, and when the page size is increased, now more bits are visible.
Okay.
Yeah, so then they stage this kind of attack at last level cache. Otherwise, staging this kind of attacks is also very difficult.
Makes sense.
So yeah, so this was the finer detail which I was looking at, but now I got it, like how they are able to stage it.
Okay.
Because otherwise, what the analysis says is, let's say if there is a 2048 set associative 16-way set associative cache, right? 2048 sets. So we need 11 bits. Attacker needs all the 11 bits should be visible. But when they do the calculation, only 5 bits are visible. So out of 2048 sets, the attacker has only 32 sets in his control. And
Okay.
if the victim is not accessing that 32 sets, then anyway the attacker's whole efforts are in vain, right?
Right.
So
Right.
what it does is it tries to cover up more and more bits. So even if 8 or 9 bits are visible, still 512 sets are in control, and that's how he tries to control.
Okay. Okay. Makes sense.
Yeah, yeah. So yeah, so that was my take on this page translation, but I think there are much more attacks. I have not read the literature, but as you mentioned, there are many more attacks, I think, on that angle also.
Yeah. And with respect to page table, just from the basics, each process will have its own page table. They are not sharing it.
Right.
So this notion of evicting page entries of some other victim program, etc., will fail.
Right.
Yeah. So
Right. Yeah. Yeah. They are, the structure itself is not shared.
yes. Yes.
Yeah, but just a quick reminder on this point. Actually, there was one paper in the Security and Privacy SNP conference. So basically, what these attacks try to do, they assume that the last level cache is inclusive, right? So
Okay.
this cross-core back invalidation thing, which everyone was exploiting, that although attacker is evicting something from the shared last level cache, still
Okay.
the victim's private cache's blocks are evicted because of the inclusion compulsion.
Right.
So they say that if we make cache as exclusive, this kind of attacks will fail. But this paper in SINP 2021, what they say is, although the cache is exclusive, but they say that the cache hierarchy, the cache directory, which maintains some
Coherence.
coherence issues and some other bits, they say. So they stage an attack there because that is shared, and they forcefully evict something from there, and now it is in last exclusive cache.
Acha.
Yeah, they exploit that principle. So even if level 1 it is not shared, they will go to level 2 and force something to come from level 2 to level 1.
But These are private, so how do they force the activity on the private caches?
They are exploiting some feature of the cache directory. Actually, I forgot it. Yeah, they are doing it somehow.
Okay, so can you
Yeah.
please share the paper in the classroom?
Yeah,
It
yeah.
will
I will.
benefit everyone.
Yeah, yeah.
Yeah. Okay.
Yeah.
Yeah,
So
please.
what I will do now, I will just complete this thing and then I will share it.
Yeah, no problem. Continue.
Yeah, yeah. Okay. Yeah. So let's look at quickly. So what is the solution here? So the solution is periodically changing the keys and performing dynamic remapping, right? And the mapping should be based on new keys, and new random keys should be generated after every time interval. So so this is an outline. So in the interest of time, I will just go to the next slide, which also considers this. So what happens is after every time interval, so let's say from t0 to t1, there are two keys which are functional. So this encryption and decryption is happening on two keys. So there is one current key and there is one current key and there is one next key, right? So after every time interval, which we call an epoch, right? So after every epoch, what will happen? The next key will become the current key and a new next key which will be generated randomly, right? So the cache will operate on both current key and next key. So let me explain why they are trying to implement this in such a way. So they are using both keys. After every epoch, the values are changed. And so here comes the crucial implementation detail of the paper, right? So what they do is they maintain an access per line remap. So this is their policy, right? So to implement this policy, what they are doing is it uses the set relocation pointer just to know which particular sets have been remapped, and it uses an access counter. So in the paper, what they have mentioned is the access counter value is set to 100. So ideally, after every 100 access to a particular block, that block will be remapped. That is, it will again go through the encryption process and it will map somewhere else. So after every 100 access, so that means the remap rate is 1%. So let's look. Now I will request everyone to please focus here, because this is the most important part of the paper. So let's see whether the cache is initially, this is the particular set associative cache. This is the initial status. Here A0 means which is mapped with current key, and whatever is subscript A1 sorry 1, which means it is mapped with next key, right? Now the counter value is 0 and we are in the first epoch ID, right? So and let's say the set pointer is in the beginning. So nothing will happen, right? Now what will happen is when the so after every 100 access to a block, the block is logically it needs to be remapped. So for this particular set, the access will be 200, right? As this is a two-way set associative cache. So after every 200 access to this particular set, what will happen is the entire set every block will be removed, which means it will be invalidated, and then it will again go through the encryption address and it will again map. So in this example, what they have done is this A0, right? So this A0 is mapped here A1, right? And then this B0 is mapped to B1. Here B1 means 1 is the next key, so it is mapped with next key, right? Now the set pointer comes down, right, to the next set. Now what is the status? A and B has been moved, right? Now let's say the ACTR value, the counter value is 400, right? Now which means more 200 sets have been accessed. Now what will be the situation, right? So now this needs to be remapped. The blocks in this particular sets needs to be remapped, right? Now here is an interesting thing. This x0 is remapped to this particular set, right? That is fine. But now this b1, right? This b1 was what? This is the block b. It was first mapped with current key. Now it is mapped with next key. Now if the set pointer comes down, do we have to remap it again, or do we don't have to remap it? So the answer is we don't have to remap it because it has already been remapped. So the option is we have moved X, but B is not remapped, and it is already remapped with next key. So the B block will stay here. It will not be remapped, right? So let's say there is the counter value rises to 600, So the set pointer decreases. Now y0 and y and a needs to be remapped, right? Y is mapped with current key and a is mapped with next key. So the block which is mapped with next key is not remapped again. Only the block with current key is mapped, right? So y will go to this particular place, right? So this is the crux, that how they are dynamically remapping it after every counter value. So if they don't do this, then it is prone to attack, right? So let's look at the last epoch. So here you can see now the blocks of this particular sets needs to be remapped. So z is mapped with current key and y is mapped with next key. So only the current key block will be remapped, right? So y1 stays at the same place. This particular z block is remapped to this particular set, right? So now what happens is the set pointer has again came back to the initial position, right? So what was the impact here? When it again came back to initial position, you can see in this yellow color in this block. This means now the blocks of entire cache, the entire cache blocks have been mapped with current key, next key, right? This one value you can see. So this one value means the entire blocks is mapped with current key. So now you can see the epoch ID has been incremented to 1. So this was the first epoch, which means in this particular epoch, in a phased manner, all the blocks in the sets are remapped, right? So this is their concept. Now again the counters will be saturated, it will be set to 0, the epoch ID will increase to 1, and again the same process will follow, right? So here the main point is what value to choose. As one question was asked by Dr. Kalyan regarding the banked session. So if the LLC is banked, so this particular value needs to be reduced. But now what are its impact? If we frequently do this, right, instead of 200, let's say make this value 20. So anyone, can you give your inputs, like what would be the impact if, let's say, this value will be 20? Let's say after every 20 access to a particular set, we are remapping it.
I had a question. How does the decryptor know what map to decrypt?
What? Sorry, Navneet, I couldn't
How
hear
does
you.
the decryptor knows that it is A0 has become A1 while X0 is still X0 at 200 counter?
Yeah. That's a very good question. So it's not about a decryptor. It's about remapping, right? You are asking about the remapping process, right?
Yes.
Yeah. So that's a very good question. So actually there are two implementation details here. One is you maintain separate bit, right? So you are using two keys. So you use one bit, right? So if that bit is value 0, then it will be mapped with next key, or if it is 1, right, it mapped with current key, right? So this is the simple issue. But one more important the most important point would be the set pointer, right? So if the set pointer is here, right, and there is another block, so this means that this particular block, the set pointer is here, which means it has been already remapped. Now it is coming back, right?
Yes. Okay. So it is necessary that if set pointer moves down, that none of the A0 and B0 will be mapped to original set, because it is random. So it might happen that A0 and B0 are remapped to the original set.
Yeah, but the chances are very less.
Yeah, but still possible.
Yeah.
Yeah, Navneet, just to add to what Prathamesh answered, this, even if it gets remapped to the same physical location, the set end way, right? The problem we would get is, or if the attacker is still able to identify it within one epoch itself, right? Because the moment we go to another epoch, its remapping can change, because the key itself will change, right? If so, within one duration, even if the remapped block is still sitting in the same physical location, the attacker's time window is reduced to one epoch. Does it make sense?
Yeah.
Yeah. So coming back to Prathamesh's question, so if we reduce this counter value, what will happen?
Yeah, so Upasna has mentioned something in the chat. She says more time would be spent in remapping. It will decrease the performance. Yeah, that's perfectly the answer, Upasna. Yeah, that's right. Yeah. So that was the performance aspect. Can you comment something on the security aspect as well?
It will enhance security by reducing time window. Correct.
Yeah, right.
Yes, it will enhance. Yeah.
Yeah, right. Right. So that's the trade-off which they are playing. So that is the trade-off. Eventually, it boils down to this only, that what should be the remapping window, and how it has to be somehow other calibrated. So yeah, so just a summary, a quick summary. Conflict-based cache attacks can be mitigated by randomization and remapping of the sets. The rate of remapping usually determines the trade-off between performance and security. If the remap rate is high, I think we have already covered this. It is difficult for an attacker to create an eviction set, but it degrades the performance of an LLC as it is busy, in remapping. And the advantage is there is no dependency on operating system. So, yeah, Kalyan, I think in a brief I have covered this CEASER.
Yeah.
I think we can,
So just
ponder
to,
much. Yeah.
yeah, go on. Just come. You can complete.
You were saying something?
Yeah, I'll tell. You can complete your point.
Yeah. So what I was suggesting was, I think we will not jump onto Damru now. Uh, we can probably, just spend some more time, some 5-10 minutes, just some question answer here, so that I think.
Yeah, and one other point is this CEASER would be the the paper reading assignment for everyone. So go through that, write your summaries, and when we discuss next time on this, it will be better. Okay. Right now, Prathamesh has given the crux of the paper anyway. Now, if you go through the paper, you will be able to connect a lot of dots. Yeah. Um, yes. So one point with the performance aspect, right? What is the impact of remapping? What does remapping actually mean? Is let's say a particular block is there in set number 10 in way number 8. Okay, and what we are looking at is its address, right? But there is another performance impact also. See, Prathamesh, we don't have the um, the index part of the address, right? So
Uh-huh.
set number 10 itself will act as a key, is it? Not key, the address, is it?
Yeah, yeah.
Now, will the tag bits also change after remapping? Should they change? Two questions.
Uh, okay. Tag bits.
Hmm.
Mm. Yeah, I
So
think I think
uh,
the tag bits will be
think,
changed.
think on that. I'll give the context to others. See, in the typical data array tag array arrangement, the uh, the set number is identified by the requested address. Okay, and we store the entire block of data in the data array, and we store the remaining bits after removing the block offset and the set index as tag in the tag array. Right now, what is remapping doing? Is it changing both tag and index or only index? So that is the question I'm asking here. Ramesh, go ahead.
So your question is absolutely, spot on. Actually, I think I was also confused there, but I saw that it is mentioning it is converting B bit physical line address to a B bit encrypted line address.
Um,
So the entire physical line address means the entire address is mapped with a key. So even the tags
So
have
both
to
the
be changed.
tag and index both are changing, is it?
Yeah. I'm not sure. I think I should cross check it, but as far as I think that
Now,
is.
okay, one follow-up question. If we are using the tag and index bits and trying to remap, okay, let's say there are 4 blocks in the set number 10, and I'm using their addresses to generate a new set number. Will it be same or different? I'm using the same key, right? The index is same. Now the tag address will not be used anyways to remap. I mean, remap means to different set, the set number, right?
Right.
So if these 4 blocks are remapped, there is high likely chance that they'll be remapped to the destination set, which is same, right? Or what am I missing here?
No. So yeah, so the point is they will not be remapped to the same set.
Why?
Yeah. So how? So can you please repeat it? So you are saying that, let's say, wait a minute. I will just share it again. Yeah. So the point is, what you are saying is this A0 and B0, right? If that gets remapped, right?
Right.
So that will go into same set, you are
Same
saying,
set.
right?
Yeah. Why are
No,
they not
no.
going basically?
No, they are not going there.
Why?
Because they have changed the mapping, right?
But mapping will change only in the index, na? Index of both A0 and B0 is same. How will it magically differ?
No, but they are also using a key, na? That key will change it.
Key is same again. Isn't it? We don't use one key for A0, another key for B0, right?
Yeah. Sorry. Yeah. No. Yeah. So that, yeah. Sorry. I got confused here. Yeah. So the point is, actually, I think they are changing. No, wait a minute. Actually, I was also stuck in this point, but somehow I got clarified. But then again.
Yeah. So we'll start tomorrow's discussion on this point. Okay. So this is for everyone to think about. Fine.
Okay.
We'll come back to this question tomorrow.
One of Upasna says one-to-one mapping between tag and data directory will remain the same. Is it?
Yes. Yes, it will still remain the same. And Prathamesh, I want you to check one other point. Okay. So is the remapping everything changing only in the tag array or even in the data array? If it needs changing in the data array, why is there a need? These are all the implementation details.
Remapping will change everything in data array, means it will just whichever set is going for remapping, right? So let's say this particular set is going for remapping. So this A0 and B0, their data will be just invalidated. The invalid bit will be set.
Yeah, but they have to physically move the data from, let's say, your set number 1 to set number 2 for B1 and set number 2 for this A1, right? So the data is not getting invalidated. It is being physically moved in the data array from one set to another, right?
Okay. I'm also confused here. Let me.
Yeah. So let's all go back and read CEASER and try to see its implementation details a little more closely. Okay.
Yeah. Sure. I will do that.
Yeah. So it's not only for Prathamesh, it's for everyone. Even I am going to do that. Vakar is also going to do that. Yes, Vakar?
Yes, sir.
Yeah.
Sir, so one
yeah,
thing.
just a small.
Go ahead. Prathamesh.
Yeah, no, please go ahead.
So what I was thinking is that only the set is changing, right? And set is defined by the index. So I think only index should change, right?
That's what even I thought. But then both A1, B1 should be mapped to the same set. Yeah, because the key is same
that is
and
true.
the original index is same. So they are using some additional bits and doing something. And on the follow-up question I had is this entire remapping only changing in the tag array or even in the data array also? Because changing something in the data array is very penalizing. because the data is 64 bytes and tag is hardly 20-30 bits. Yeah.
Yeah.
So if there is a need to change in the data array, can we break it? Because anyways we are looking up the tag array. Yeah, so think on these lines, because implementation of such an key based remapping and everything is not so out of the box idea. It's more or less a straightforward one. But yeah, go on, Kishore.
So the changing part would be only index, but to calculate the new positions of A0, B0, we need to access the block offset, right? So we
Right.
don't need to change the block offset. We just need to calculate the new positions.
No, block offset is not stored at all.
But
We are storing the entire 64 bytes, isn't it?
yeah,
So the entire cache block is
okay.
stored. So the block offset is kind of zeroed out, more or less.
Okay.
Yeah. I think I have missed some important details here. I think that set thing, actually I got it cleared, but yeah, but this I am sure of, that it is not mapping to some set, so they might be using something else.
Yeah.
Yeah.
So how they are doing that, we'll study. Okay.
Yeah. Sure.
Yeah. Okay then. So we'll meet tomorrow.
Yeah. Okay. Yeah. I will stop presenting.
Yeah, and I'll stop the recording part.